So question 4 on the spectroscope. The speed of light is given there, and we have a spectroscope fitted with a diffraction grating being used to observe the spectrum of excited helium gas in a laboratory discharge tube. One first order bright line of wavelength 587.563 nanometers is observed at a deviation of 20.6426 degrees. Very precise, lots of significant figures. So these are very careful measurements. And A is calculate the number of lines per centimetre on the diffraction grating. So that's quite a mathematical question, but just to give background, this is dealing with emission spectrum of the spectrum of light coming out. The emission spectrum is light that is emitted from excited gas, and what happens when you excite the gas, either with heat or sometimes through electricity, you make the electrons jump into higher energy levels. That is, they require more energy to sustain those levels, and when they drop back down, they give off a photon of light that is equivalent to that energy gap. That's what's going on. In any case, light is given off by an element of helium gas in the lab, and what's going to happen down below in this question is you compare the light from the helium gas in the lab to the light from the helium gas from a star, and you can analyse and notice a few interesting things there. But anyway, let's get on with this. Calculate the number of lines per centimetre on the diffraction grating. That is N in the formula. N is 1 over D, where D would be the spacing per line, or the distance between two successive lines. We have theta, the angle here, and we have the wavelength given there. So the formula you would use is N lambda equals D sine theta, and we can use this because as a diffraction grating, where the small angle approximation doesn't apply, so we have to stick with the angle that is given exactly as is. So we have theta, we have N, because it's, I believe, the first order, there we go, first order, N, and we're given the wavelength as well. So the only unknown is D, and then we can use, once we rearrange to find D, we can then use that to find N, using this equation above. So this is a purely mathematical question. I'm not going to go into how by putting the numbers in. I'm sure you can work that part out yourself if you're looking at this level. So next part, the spectroscope and grating are used to obtain the spectrum of a distant star. There we go. So this is putting that initial first part to use, which shows a bright line blurred between 587.60 nanometers and 587.67 nanometers. This line is thought to be due to the same electron transition that produced the 587.563 nanometer line in the laboratory. Okay, so explain the difference between the lab and the stellar wavelengths. So it's a difference, so we'd probably look at what caused, well, we already know what causes the emission. We want to look at that one difference. So where to start? The key concept dealing with here is actually the Doppler effect, because as with sound waves, light waves are also affected by the relative motion between the source of those waves and the observer. So in this case, the wavelength appears to be shifted from the original to something which ranges about a centre point that's a little bit higher than. So that means the wavelength is increased, which would give us an indication that the star is moving away relative to the Earth, so moving away from the Earth. I think you're supposed to spell Earth with a capital E, as a really big planet, so we'll call it E, a big noun. No. So that's pretty much what it is. It's a Doppler effect. The source being the planet or the star is giving off waves, and then it moves away with the successive waves appearing further away from the previous wave than it should, if it was a stationary source, and the observer over here, which is us on Earth, only sees the separation of the waves as they're coming in, and slightly longer. So that's what it is.